Hi, my name is Cathy Fang, and I'm presenting ElectriPop, low-cost shape-changing displays using electrostatically inflated Mylar sheets. This work was done at Carnegie Mellon University with my colleagues Jianzhe, Professor Li Yao, and Professor Chris Harrison. In this work, we used metalized PET film, commonly known as Mylar, which costs less than $1 per square meter. Users first create their designs in a vector editing program, where our simulation shows the 3D output in parallel. Mylar can be cut with hand tools or by industrial processes. In this research, we used a laser cutter for prototyping. Then, upon the application of electrostatic charge, users can create a wide array of 3D objects that self-actuate. We're not the first to electrostatically inflate Mylar structures. Due to their extraordinary weight-to-volume ratio and their ability to self-actuate without motors, inflatable polymer film structures are particularly attractive in spaceflight applications. Within HCI, there's a large body of work focusing on shape-changing displays. Some were inspired by origami and kirigami techniques, while others use air pumps for pneumatics and linear actuators that are generally noisy and consume significant power. Other methods leverage physical properties that change the material structure to achieve shape change. Most related are methods employing electroactive materials such as dielectric elastomers that compress membranes, which cause a structure to bend or displace liquid. ElectriPop works based on the simple principle of Coulomb's law, where objects with like charges repel from one another. When a charge is applied to the system, the electrostatic force causes the conductive film to hinge upwards, popping up from the conductive base. Then, when we introduce a cut in the film, the structures inflate to find an equilibrium between the repulsion force and the material's elasticity resisting the deformation. Based on this principle, we created a set of design primitives that serve as building blocks for creating interesting 3D forms. A slit, which we define as a cut joint on both sides, causes the Mylar to form a loop. Many slits can be cut, creating an array of ribbon-like features that repel to create a sphere-like structure. Flaps are a special type of slit, where the cut creates an enclosed area which is repulsed by the main body. Flaps can also be nested and arrayed to create complex 3D forms. Finally, the silhouette of a design can be varied, along with interior embellishments to add details. For actuation, we created two proof-of-concept digitally controlled static generators. The one on the left is built around a miniature Van de Graaff generator controlled by an Arduino, while the other uses a transformer and a Raspberry Pi. The transformation from 2D to 3D is not always intuitive, so we built a simulation tool that works with a vector editing program. We have open-sourced our simulation tool and provided some example designs for those wishing to try. We used our workflow to create a series of illustrative demos. For example, the flower we designed could be used as an ambient display. The level of wilt can be coupled with a dynamic value such as stock index or household water consumption. Different physical elements can be individually actuated as seen in this weather forecast ambient display. We envision smart speakers with pop-up avatars. By varying the actuation voltage, we can create rudimentary animations, such as this avatar trying to draw the user's attention. Swappable accessory tops could allow for inexpensive avatar personalization. The flat geometry of our designs means that they could be mailed and used for pop-up holiday cards, such as this Christmas tree. We can enhance existing objects by adding actuatable interactive elements, such as decorative wings and streamers on this Quidditch trophy. Finally, we can create pop-up books and other more immersive educational experiences. Here, a squid attacks a fish, while on this page, a clam on the reef opens to feed. In order to compare with other shape-changing methods, as well as more deeply understand the physics of our technique, we characterize ElectriPop's behavior using our snowman design. The average steady-state current needed for the power source and for inflating the Mylar are under 7 microamp, which is well below the international standard's energy source limit. As the Mylar charges, it begins to repel and overcome gravity and air resistance. On average, our snowman design takes around 100 milliseconds to fully inflate. We also measured how the structure electrically deflates when there is a forced discharge. The discharge happens under a fraction of a microsecond. The system's estimated storage charge is around 16 nanocoulomb, and the capacitance is on the order of tens of picofarad. Both are extremely small compared to the IEC standard. Once discharged, deflation is assisted by gravity and stored spring forces, so the structure took less time to fall compared to inflation. We compared our simulated result against the real-world output and measured an average 3D Euclidean error of 1.55 millimeters. The simulated form is mostly accurate with small regions of variation. The simulation convergence time depended on the size of the design and overall was near real time. During our user study, participants appreciated that they could see the simulation results in parallel and save them time during iteration. We compared ElectriPop with other shape-changing systems across a range of important criteria, and please see our paper for details. Overall, our use of electrostatic force as the actuation method is unique. ElectriPop's use of a single layer of bulk material permits low cost and quick fabrication while still offering creative outputs. Furthermore, our technique doesn't require exoskeletal structures, allowing the system to be transportable and lightweight. ElectriPop's shape-changing effect is near instantaneous. Once inflated, our forms can hold their state for long periods of time, which is energy efficient. Unlike most motor and pump-based systems, our technique is essentially silent in operation. Now I'd like to address the limitations of our system. Humans naturally accumulate electrostatic charge. Nonetheless, our use of static charge makes touch interaction less desirable. While we do not encourage users to make contact with mylar structures when electrostatically charged, there is an interesting effect wherein the mylar leans towards the user's hands or body when proximate. Our system demonstrates complex volumetric shapes, but we couldn't achieve shapes such as a cube or cylinder or actuate structures taller than 40 centimeters. Future work could explore multi-layered forms with structured joints and hinges. Although our simulation tool helps to speed up iteration, the overall design process is still very much trial and error. A semi-inverse design tool where a user could directly modify the desired 3D form will be valuable. Lastly, due to the material property and the operating principle of our system, the final outcome is subject to changes in airflow and humidity. To summarize, we have introduced a new shape-changing display where 2D flat-packed mylar sheets can be inflated into complex 3D structures using electrostatic force. We introduced a design vocabulary and developed a simulation tool to facilitate rapid prototyping. We created a series of demos such as ambient displays and educational pop-up books. We hope this work inspires new and creative shape-changing interfaces. Please see the paper for more details. Thank you.